Hopefully you just completed the activity about how volcanoes look similar and how they look dissimilar, because this sort of logically follows that particular activity. There are three primary types of volcanoes. Some textbooks divide them into more, and this is just kind of a way to look at them in a very broad scale to see what are their big differences. So I like starting with this slide here because you can see the profiles of the three distinct type of volcanoes. So the one that probably stands out the most is this very large volcano, and that's called a shield volcano, and that's what we see in Hawaii as well as many places around the globe. So we're going to talk in detail about each three of these types of volcanoes. This is a composite cone volcano, also called a stratocone, and then the very smallest type of volcano is called a cinder cone volcano. And these are the three types of volcanoes that you actually looked at for your previous activity, and I'll be referencing them throughout the lecture today. But I wanted to show you these sort of side by side. So these are examples of sort of representative types of each type of volcano because they do vary significantly in size and in shape. So let's get started. This is the picture of Fernandina, which is a volcano in the Galapagos Islands. This is actually a very similarly shaped volcano. This one is in Hawaii. This is Kilauea, which is the most active volcano on the globe. Both of these are examples of what are called shield volcanoes. Shield volcanoes are common in ocean crust, like both Fernandina and in Hawaii, but they're also relatively common in areas where the continental crust becomes relatively thin. They are very broad domed volcanoes, incredibly large, like in some cases almost 100 miles in diameter, but they're relatively gently sloping. And they're gently sloping because they are primarily composed of basaltic lava flows. You'll be learning more about that this chapter. Basaltic lava flows in general are very runny, and they're dark in color, which you can see in the picture in the foreground here of Kilauea. Because it's runny, they tend to flow very far from their origin and in thin little layers. Here is another picture of a lava flow in Kilauea, and you get the sense that this basaltic lava just accumulates one layer on top of another. The summit of these volcanoes, because they are so large, the summit is called a caldera. A caldera is the summit of a volcano that is larger than 1 kilometer in diameter. That's honestly a pretty randomly determined number, but that is what geologists refer to as a caldera. You'll see that not all volcanoes do. Smaller volcanoes do not have calderas. There's fantastic imagery of the caldera in Kilauea collapsing and swelling and then collapsing as there are pulses of lava that come to the surface in Kilauea. It's great. So what happens is in this photo below, you can see one of these active basaltic lava flows. And as you might imagine, the surface of it is in contact with the air, which is much cooler than the interior of the lava flow. So what will happen is that the surface of the lava will cool first and create this really cool texture that you'll learn about later in this chapter. But what ends up happening is the warm center continues to flow, and it will continue just to flow downhill because lava is not free from the force of gravity. So it keeps flowing downhill, and it leaves behind this sort of crust, and it forms really cool features that are called lava tubes. So this is a picture inside a lava tube. This used to be the surface of a lava flow, and it cooled, and then the lava flow actually continued. In this particular case, it continued to flow that way, and it left a tube behind, and eventually the lava tube collapsed and it created this cave. And they're very cool. These are relatively common anywhere that you have shield volcanoes or basaltic lava flows. Lava tubes are home to bats and all sorts of little creatures that can get down in there. This particular lava tube is one of a network of lava tubes at a place called Craters of the Moon National Monument in Idaho. And here I'm walking on the surface of that lava tube, and you can get a sense of how the lava flowed. And then the surface collapsed downward and you can climb down into it. It's actually super fun. It's very sharp. The rocks are incredibly sharp. I have a sweet scar left from a sharp part of the lava tube. But just to kind of put this in framework, here's the state of Idaho, and this is Craters of the Moon National Monument. Just for perspective, Yellowstone National Park is right here. And this whole part of the Snake River Plain is an area where the crust of the earth is incredibly thin. You can see that topographically, even this is a really low-lying area. That's actually related to the Yellowstone geo-ecosystem that we'll learn about later this semester. But because the crust became so thin, there was a big outpouring of basaltic lava in this area. And you can actually see some smaller volcanoes in the background, and that's the third type of volcano we'll get to in just a minute. All right, this was the second picture that you looked at. This is Mount Fuji. Mount Fuji is a classic composite cone volcano. And here is sort of the anatomy of a composite cone volcano. You see it has a central pipe or conduit where you have a series of layers that are built up there. It's called composite because it's composed of different types of material. It is composed of lava flows, which are these darker colors here. In general, we'll learn about these are called andesitic lava flows, and it's also composed of pyroclastic material. Pyroclastic material is hot surges of ash and gas and debris that are incredibly destructive and shoot out of volcanoes that are composite cones. Composite cones are cone-shaped. They are very steep. They are, and again, typically composed of pyroclastic flow deposits and andesitic lava flows. And you will be watching videos of these both within lecture, and then there is a longer 50-minute long, I believe, video of volcanoes where you'll get to see pyroclastic flows in action. They are incredibly destructive but totally fascinating. And actually, if you are keeping track, there is a big eruption going on in the Philippines right now, and that is an example of a composite cone volcano also. So composite cone volcanoes are incredibly destructive. They are unpredictable, not totally unpredictable. They can be predicted if you look at if they're continuously monitored, and geologists can note the frequency of earthquakes, the magnitude of earthquakes. We can use all sorts of tools to map the magma in the subsurface so we have some idea of how close they're getting to the surface. But because they have high gas content, which is what creates these pyroclastic flows, they are prone to really explosive volcanic activity. And so for that reason, they are relatively dangerous. Each one has its own sort of cycle. Some erupt with some regularity, some erupt mostly steam, and some erupt, and there can be hundreds of years between eruptions. And when they do erupt, you don't know if it's going to be a small eruption or a devastating eruption. Also associated with composite cone volcanoes are hazards called lahars. So I'm going to go back for just a sec. If you look at the top of Mount Fuji, you'll notice that there are glaciers and snowpack on it. So as you might imagine, when there are eruptions beneath those glaciers and that snowpack, it melts and it creates a tremendous amount of water. There's usually electrical storms, like lightning storms and thunder and lightning storms, that are associated with volcanic eruptions anyway, because there's so many charged particles that are shot into the atmosphere at that time that water droplets will actually form around those ash particles and bring them back down to earth. But then also the melting of glaciers at the top of volcanoes will create a tremendous amount of water, and lahars are examples of what are called volcanic mud flows. So here is a river valley. This one is in Peru, and you can see that in this river valley, a lot of these rocks are volcanic in nature, and here is a river that is existing on the flanks of the volcano, and there was a lahar in this area. You can see some of the ash and some of the damage from the eruption in the background of this. It melted one of the glaciers, created a tremendous amount of water that then rushes down the slope of the volcano, and it basically overflows stream valleys on volcanic slopes. In a lot of places, there are many, many, many cities that are built along these rivers because they were primary sources of drinking water and irrigation for, in some cases, thousands of years. And so lahars are often very deadly to people. It's a mixture of water as well as a lot of that volcanic debris, much of it ash, and so it will overflow the banks and oftentimes just wipe out whole towns along these particular areas. In fact, when we started the semester, we talked about Mount Rainier being the most dangerous volcano in the United States for this very reason. Mount Rainier has 20 glaciers at the summit of it, and Rainier is an active volcano, and there are many, many, many lahar flows that have been mapped down the flanks of Mount Rainier, many of them going directly beneath the city of Tacoma, Washington. And here it is. Here she is, lovely Mount Rainier. And so, yes, again, Mount Rainier, composite cone, 20 named glaciers prone to lahar flows in the state of Washington. And just south of Mount Rainier, in the same volcanic system, is Mount St. Helens. Mount St. Helens is the only composite cone volcano to really erupt in modern history in the United States. Mount St. Helens erupted in 1980. Mount St. Helens was a really interesting eruption. There were evacuations. There were 6 months of increased seismic activity and steam. And so there were evacuations of Mount St. Helens, given that even those evacuations, there were 50 people who died, many of whom just honestly refused to evacuate. But what's cool about Mount St. Helens is that it didn't erupt out the summit like most composite volcanoes do. It actually, in the weeks that preceded the eruption, there started to be a big bulge on the north slope of Mount St. Helens, like right here, and it didn't erupt out the top. It actually erupted out the side, more of a lateral blast, and you can see that the summit of Mount St. Helens was lost during this eruption. And you can see all of these little streams that flow down along the flanks of Mount St. Helens are actually cutting down through layers of volcanic ash. So both of these are part of what's called the Cascade volcanoes, which run through Washington State, Oregon, and Northern California in the great United States. Other noteworthy composite cone volcanoes include Mount Kilimanjaro in Kenya, and of course Mount Fuji that we saw on our previous slide in Japan. Cool. So, one other very famous composite cone is Mount Vesuvius. And these pictures I took several years ago in Pompeii. And my great story about Pompeii is that I was attempting to speak in Italian very unsuccessfully to a train conductor, and I just eventually gave up and spoke in English. I told him I wanted to go to Pompeii, and he told me to get off of the train at New Pompeii, or Pompeii ruins rather, not New Pompeii. And I said, "What is New Pompeii?" And he said that is where they built a city after old Pompeii was completely buried in volcanic ash from Vesuvius. And I said, did they know what happened at old Pompeii? But this is a reality of living in an area where there are active volcanoes, and the Italians do it and have done it for thousands of years and do it beautifully, in fact. So I want you to know that these streets that we walked here were completely buried in volcanic ash. And since the 1800s, Pompeii has been under continuous evacuation. There are all sorts of archaeologists there still today that are slowly helping this buried city emerge from volcanic ash that was deposited during a huge pyroclastic flow down Mount Vesuvius in 79 AD. Mount Vesuvius is Pompeii is very famous for the casts of people who were created after this volcanic eruption. So the people basically saw this huge ash blast come down the slopes of this volcano towards their very large city. There was a city of over 20,000 people 2,000 years ago, and they were buried alive in ash. And when archaeologists first discovered this, they found these large holes, these cavities in the volcanic ash, and they poured plaster down into those cavities, very carefully removed the ash, and found these outlines of people, these casts basically they made of people who were buried alive. And they've been moved since to the city of Naples in Italy, where you can see them. But they're still being extracted, to be honest, still in Pompeii. These are some pictures from some of the building materials that were used to build Pompeii. And one of the things you'll learn in this chapter is that the materials that you see here actually are super indicative of violent volcanic activity. A lot of times when you see volcanic rocks that have holes here from escaping volcanic gas. Volcanic gas usually means that your magma chamber is under a lot of pressure because it has a really high gas content. So this is a big clue that this volcano, when it erupts, is an angry volcano. And then this rock over here has two grain sizes. It has a texture called porphyritic texture. And these big grains, they form when the magma is just kind of chilling inside the volcano, maybe for hundreds of years. And so you think the volcano is extinct. And then when the volcano erupts, it carries up these particles that have already cooled, and then the rest of the rock cools quickly. So this tells you that there's often hundreds of years. If you find a rock like this, it means the volcano you're near will sit for hundreds of years before it erupts, and when it does, you don't always know quite what to expect. So composite volcanoes are super cool. When they erupt sometimes, they actually will create calderas. Typically, composite cones have craters. Craters are summits of a volcano that is less than 1 kilometer in diameter as opposed to a caldera. So an example, to go back to Oregon in this case, back to the Cascade volcanoes, is a park you may have heard of called Crater Lake National Park. Crater Lake National Park actually started its geologic history as Mount Mazama. Mount Mazama was a composite cone volcano. It's your classic cone-shaped volcano, and it had a violent eruption. I believe it was about 7,000 years ago. When that happened, part of the magma chamber emptied out, and enough of it emptied out that it became structurally unstable. So if you look, here you have an entire volcano sitting over this very large, for all intents and purposes, cave. So what happened was the surface that which was holding up the volcano collapsed down into that volcanic chamber and created this very large caldera and the collapse of Mount Mazama. Then there's some incidents where some of this molten rock still kind of eased its way up through fractures. There's some small little inactive volcanoes inside Crater Lake, but then over about a period of about 700 years, Crater Lake filled, because it's basically a giant bowl, filled with precipitation and created Crater Lake that we see today. And the water is some of the bluest water in the world. This is the deepest freshwater lake in North America at just over, I think, 1,900 feet deep. So here is the crater of Crater Lake, and Mount Mazama, the remains of it are beneath it. This is a very small volcano that formed from some of that residual volcanic activity. Good story. All right. So our last type of volcano you see here, it's much smaller. It's called a cinder cone volcano, and they are just adorable. I'm going to show you an image called if it wants to open for me, called a gigapan. Gigapans are super cool. Okay, I'm dragging it over here so you can see it. A gigapan is actually thousands of pictures that are taken by a robot at different focal depths. And then they're kind of stitched together by a computer so that you have tremendous capabilities for zooming around a landscape. So here is a cinder cone volcano. This is called Lava Butte, and it's in Oregon. And if you zoom in to the cinder cone volcano, you can see something kind of cool. Isn't this crazy? So close. Cinder cone volcanoes are actually just composed of like a pile of rocks. They're called cinders, and they're not particularly high. Cinder cone volcanoes don't get to be more than about 200 feet high. This particular one had a cool lava flow. This gigapan was created by the late great Ron Schott, who was a geologist who saw the value in this technology. He got money from the National Science Foundation to basically drive around America and gigapan the heck out of it. And he is responsible for, oh, is that a chipmunk? I've never noticed that before. Look. So Ron got paid to gigapan lots of really cool geology. I had that opportunity to meet him a few years ago. And when I met him, he was a really nice guy, but I also got to see these fun little guys, Ed and Edie. Where did Edie go? Oh, there we go. And he puts all of these in he put all of them in his gigapans for scale. And they're about 4 or 5 inches high, but you can see like some of the flow on some of the textures of the rock. Gigapans are just so cool. So if you go to gigapan.org, and the link will be in this slide, basically you can just zoom all around America. It's so cool. Anyway, so I got off topic here, but this is a cinder cone volcano. Let's get out of here. All right. Cinder cone volcanoes are small, steep volcanoes. Very often they will occur in little groups, and I'll show you why in just a second. They are built from small pea-sized rocks that pop out of this particular type of volcano that are called cinders. So again, cinders are about the size of like a pea or so, maybe a little bit bigger. And the reason they occur in groups is because they're basically a pile of rocks. So you will have a small cinder cone volcano here with a central vent, and it's almost like popcorn where they just kind of pops out of the earth and they will accumulate in these small steep-sided volcanoes. Eventually they can get clogged with rock fragments. So then what will happen is that the magma chamber will find a fracture in the subsurface, and then another cinder cone volcano might pop up like right here. So they often occur in groups. They don't necessarily exist for very long because they get clogged and then another one will form. This is a cool story. This is a cinder cone volcano in Mexico. It's called Parakuten. And this was one of my daughter's old favorite bedtime stories. It was when I worried that she might be a serial killer because there was this Volcanoes book that I loved that she loved, but this was her story. So there was this Mexican farmer, Dionisio Peludo, and he went out to his crop one day, and the ground was really warm, and it was a little bit higher than normal. And he went out a couple days later and there was a crack in the earth and there was steam coming out of it. And just a few days after that, some of these cinders started popping out of the earth and built a volcano that is pictured here in the background. And over a period of 2 years, the volcano grew and grew and eventually started producing lava flows. And it produced enough lava flows that it actually buried everything in Parakuten, Mexico, except for the steeple of the church. So while cinder cones are typically not particularly destructive, they certainly have their moments, like we see here in Mexico. So this is actually back at Craters of the Moon National Monument in Idaho. This is one of my field classes. This is Professor Barone, who is the other geologist on staff at MCC. And one day we took students to Craters of the Moon. We teach a class called Field Studies in the Geosciences, where we go on location every year. We usually do it in the spring and we go on location in the summer. And like half of Craters of the Moon was closed for construction, which was disappointing. So we needed something to do. So we're like, hey, let's climb this little cinder cone volcano. They're small, and they are small until you start hiking them, and then they feel very steep. So you can see here all of the basaltic cinders. There we are climbing up and up and up. And everyone made it to the top, and only one person had an asthma attack, and I'm happy to say that person wasn't me. But these are a series of cinder cone volcanoes. You can see this one's older. It's been eroded and there's soil, and now there's actually vegetation on the surface of it. So this one is older, for example, than this one right here. And certainly it's older than the one that we're hiking on. Let's see. And these are some of my old students. This is Farrell. Farrell is a geologist in Denver right now. This is Johnny. Johnny is a geologist in Oregon. And this is Kara, and she actually works in government land use in Westchester, New York. Anyway, cool stuff. Cool geology. So those are basically the three types of volcanoes. They're not randomly distributed though. So just for a reference, here's Parakuten. We were just talking about that one in Mexico. Here's Vesuvius in Italy. Here's Mount St. Helens right here. And then this one most likely is Mount Rainier. Kilauea in Hawaii. And here are the Galapagos Islands for Fernandina. And I think that is the majority of the ones. Oh, in Kilimanjaro, the composite cone volcano in Kenya. So volcanoes are not randomly distributed. They occur in very distinct places. Many of them occur around the Pacific Ring of Fire, which we've mentioned earlier. It's a big series of convergent boundaries where ocean crust is subducting beneath other plates. But it's not just around, there's a ton of volcanoes around the Ring of Fire, but not all of them. Some are over here in the Caribbean, where there's a small plate boundary here. The ones in Iceland are part of a plate boundary that occurs here. There is a divergent plate boundary that exists beneath Africa, and that creates all these volcanoes here. And this is a big convergence zone, which creates these volcanoes here. Down in the South Sandwich Islands, this is another small convergence zone. So, in general, the location of volcanoes is not random. Most are near plate boundaries. There's very few that aren't. Kilauea and Mauna Loa are examples of ones that aren't, and that's because these are special situations that are called hotspots that you'll read a little bit more about in your textbook. But that is pretty much it. This is what types of volcanoes are there and where do we find them? All right, thank you.